So I looked up how to take a good selfie on the internet and deleted it from my search history out of embarrassment. But one of the things that I read is I'm supposed to put the camera up really high, and that somehow makes me look slim. So I put my camera up on the roof. It was too small. We are talking about causality. This is not a time travel film. This is not a physics class. But we need to talk about how we can establish causality. In other words, how can we try to build a case that one thing caused another, that X caused Y, that A caused B? And to a great extent, this is the holy grail of science, not just psychological science, but science in general. I picked the weather background for this slide. It's somewhat mysterious, but because I was thinking about how complex psychological science is, to try to come up with a cause. One variable causes something. How difficult that is. And I was trying to imagine a science that was similarly difficult in that way, and I came up with weather. My brother-in-law does the computer modeling for the Canadian version of the National Weather Service. He's a big, giant, smart nerdball guy. Heck of a hockey player, though. He's Canadian. And he talks about the complexities of those models and how everybody's so mean about them when they're wrong. Well, psychological science is kind of that way too. To try to understand behavior, to say that X caused Y is very, very difficult. But we have some ways we try to maximize our ability. And so we're going to talk about how to do that, the methods to do that, and also ways in which you can't do it, despite people trying. I should sit up more straight. I have bad posture in these videos. I'm sitting on the floor. So I want to be as tall as I can. So we're going to talk about the things it takes to establish causality. And then after this, we're going to start talking about very specific experimental methods so that you have the experimental approach you need for any given problem you want to solve. Okay, maybe if I raise this a little bit more. Is that better? Do I look slim now? Should I hold it like this? Now I look like a disembodied head. All right, let's go. So this entire lecture, and to a certain extent the entire semester, is about this, causality. Because there's lots of things you can try to figure out in science, but the ultimate one, the one that's at the heart of it, is trying to figure out what causes things. Whether it be what causes changes in the weather, or what causes a COVID-19 infection, or what causes multiple sclerosis, or what causes schizophrenia. And so this whole chapter is about understanding how one might be able to demonstrate causality. And there are three basic things you need to show. They're very simple. And so simple, in fact, it seems like this should be a piece of cake, but it is much more difficult than these three things might make it seem. The first is one we know. The first is we have to be able to show correlation. We know how to do that. We've calculated the correlation between two variables. And we also know that a correlation is simply the relationship between variables X and Y to understand how they move together. And that correlation, which is expressed as a coefficient, can range between 0 and 1, where 1 is a perfect correlation, 0 is no correlation. And that correlation can be either positive or negative, meaning the variables move together in the case of a positive correlation, or they move oppositely, in opposite directions in the case of a negative correlation. So if we're starting at the upper left-hand quadrant here, we have a perfect correlation. If you know X, you know Y. They move perfectly together and create a perfect line. You can predict Y 100% with great 100% accuracy if you know X. It's true also for a negative correlation. If it's -1, you can predict X from Y and Y from X. Now, we don't get those perfect correlations. We're lucky if we get something close to 1, and you can see two examples there. Moving to the right, an R that's close to 1. It's not a perfect straight line, but you can predict very well using it. And a close R close to -1, you can see similarly, it's going the opposite direction, of course. It's not perfect, but it's very close to a straight line, so you can make very accurate predictions. That final quadrant on the bottom right is when your correlation is 0 or close to 0. And you can see there's no line there that allows you to predict X from Y. No correlation exists. But let me make this point. Even if your R is +1, and you can predict Y from X perfectly, that's not good enough to establish causality, and we know why. Because there's lots of spurious correlations. Things like the positive correlation between per capita consumption of chicken and U.S. crude oil imports. You can predict how much oil will be imported by knowing how much chicken has been eaten. And a completely absurd correlation, but a real one. And you would be a fool to assume that somehow chicken consumption causes a change in crude oil imports. You wouldn't make that mistake. And as ridiculous as that is, it's true of every correlation. Because there could always be something else, choice, or rather variable Z, that's actually causing both of these things. So we need to establish a correlation, but that is not enough. We can say it is necessary that two variables are correlated for there to be causality, but it is not sufficient. What else do we need? Well, one thing is sequence. The order of events matters. Because two variables can correlate when X causes Y, but they could also correlate, and it'll be the exact same correlation if Y causes X. But X has to come before Y to be the cause. If one thing causes another, it has to come first. So we need to be able to establish that. That X happens and then Y happens. So correlation, sequence. Those aren't too tough. We can do that. But here's the hard one. Ruling out alternative explanations. This is a weird image. I typed into Google, video games cause violence. And I did that because a lot of folks make that claim. That playing violent video games, whatever the violent video game of the day is, maybe it's Fortnite now, it used to be Grand Theft Auto. When I was a kid, it was, gosh, what was the violent game back then? I don't even remember, I'm so old. The games when I was a kid weren't that violent. It was, Donkey Kong and Pac-Man. But nevertheless, for a very, very long time, people have said, violent video games cause people to be violent. And there is some correlation. But what we don't know is the order of events. Do violent, aggressive kids play aggressive video games? Do they seek them out? Or do aggressive games make those kids more aggressive? We don't know the order. Furthermore, most importantly, we don't know that if it's the video games making them aggressive, or some other variable that's causing both of those things. Maybe it's not a lot of family support. Maybe these kids come home from school, they don't have anyone to interact with, they don't have anyone to learn from, and so they're just playing video games all day. Maybe that's it. Maybe they have some sort of genetic or biological condition that causes them to seek out aggressive games because they're also aggressive. It would be that biological condition that was causing both. That would be the Z causing both X and Y. Maybe it's money. Maybe it's socioeconomic status and opportunity economically. Maybe it's diet. Maybe these kids don't eat healthfully and they have some impairment in frontal lobe development as a result. Look, I don't know that it's any of those. It may not be any of them at all. But what we don't know is whether it's video games or something else. Because though we may be able to establish correlation, we probably can't establish sequence, but maybe we can. But I'm really certain it is very difficult to rule out all the other alternative explanations. And so causality, as demonstrated here, is hard. It's difficult to set up a study where you're able to do all three of these things. Establish that the variables are related, establish that x comes before y, and then rule out all the potential other variables. Z, A, B, C, D, all of these other variables that might be the cause of each of these things. But just because it's difficult doesn't mean we don't try. And that's what the rest of the semester, to a great extent, is about. Trying to do our best to figure out how to establish causal relationships between variables. But I want to go right to number 3 here, because we've already covered 1. 2 is actually relatively straightforward to figure out. So let's jump to 3. How do we begin to rule out alternative explanations? No, that's what this slide says. It makes sense. It's as if I knew it was coming. Here's a term which we introduced early days of last semester. Most of you were there. Few of you remember. But the term is internal validity. Internal validity. Now, let's think about that word internal for a moment. Internal is referring to within our study. So we're talking about the validity within our study. Well, what do we mean by validity? You know that the word valid means something is reasonable or true. It sort of means the same thing here. We define internal validity as the extent to which we can say that one variable caused a change in another variable. In other words, how confident are we that X caused a change in Y? How confident are we that we've established causal relationships? That's internal validity. Now I'm going to do some things. I'm going to do this here in a kind of an unusual order, but let me put this here. Variables that vary systematically. There's a typo there. Variables that varies. Forgive me. Variables that vary systematically. With the variables that we're studying, the variables of interest, whether it be violence in video games, for example. If there are other variables like diet, like family structure, like socioeconomic status, that also seem to systematically matter, then those might be the alternative explanation. Maybe they are the cause. And those kinds of variables have a name. We're studying X and its effect on Y. But what about all the potential other variables? What about the Z's? We call those confound variables. If you ever heard someone say, I'm confounded by that, what they mean is they're confused. They don't understand. That's sort of what this means too. These are variables that are in the mix that might actually be the cause instead of the thing we think it is the cause. And so our job to establish internal validity is to do our best to eliminate those. And as we eliminate those, our internal validity grows. We eliminate 1, it gets a little bit better. We eliminate 2, it gets even better. As we are able to control or eliminate those potential confound variables, our confidence in our internal validity grows, as demonstrated by that lousy PowerPoint animation. Let me show you a really simple, almost embarrassingly simple example of a confound variable. So this is a representation of a simple experiment, or simple study, I should say, where we are trying to establish if attractiveness has an effect on likability. Meaning, the more attractive a person is, are they rated to be more likable? So we've got 2 groups. We've got a less attractive group. These are models that are not that attractive. Less attractive models? I would settle to be a less attractive model, I guess. But less attractive models, and we compare them to more attractive models. And we have our participants rate them on likability. And you can see those scores there. Pretty straightforward. And we might find that people tend to give higher likability scores to more attractive people. And I think that's probably true, though I don't know. So that's easy. So is that causality? Well, maybe. But here's the problem. We have our intended variable, attractiveness. And we want to establish that attractiveness causes likability. Okay. But the thing is, what about all the other variables? Let me give you just one simple example. Whether a person is poorly dressed or well dressed. Let me make this suggestion that if we find photos of models, there's a chance that our well-dressed models, our more attractive models are better dressed. Maybe they're modeling high fashion. Whereas our less attractive models, maybe they're modeling less fancy clothing. And so these likability scores may accidentally, systematically differ, not as a function of attractiveness, but as a function of dress. And so that variable, fashion or how well dressed a person is, could potentially be a confound variable. So, as I said, it seems easy, but because of that confound variable, we don't know if attractiveness is the cause of the change in likability or fashion is the cause of the change in likability. That's the rub, y'all. Even the simplest of experiments, the simplest of studies, we have this challenge to minimize as many confound variables and their influence as possible. So the ability to eliminate confounds is so important that two researchers by the name of Campbell and Stanley in the 60s went through and actually named some of the real common and dangerous confounds or types of confounds. They called them threats to internal validity. Now that list has been updated over the years, kind of reorganized. Cook and Campbell, for example, and then more recently some researchers whose names elude me, they're too new for me to remember, in the 2000s reorganized them a little bit. But they basically stayed the same. I want to walk you through them. First, I'll kind of give you the list and the categorization, the way they're organized, and then we'll talk a little bit about them. They're that important. So they can be divided into what are called environmental factors and participant characteristics. So environmental factors includes anything in the environment of the experiment, kind of broadly defined, that might be a threat to internal validity. Participant characteristics are anything that comes to the experiment with a participant. Anything about them that may commonly be a threat to internal validity. That'll make more sense in a second. But very quickly, we have history, maturation, testing, and instrumentation that fall here. We're going to walk through these. Over here, we have statistical regression, attrition or mortality. Two names, I'll flip back and forth between the two. Truth be told, mortality is the original name. Selection, and then also selection interactions, which is really just how any of these can interact with selection. We'll say more about that before we're done. So what I want to do is just kind of walk through most of these and give some examples as we go. So let's do that. History. And the way history as a threat of validity works is it refers to any kind of event that happens in the middle of an experiment that may differentially affect your groups, your participants. Any event or environmental condition other than variable A that caused a change in variable B. This photo's from 9/11. You guys, bless your hearts, are so young now. I can't even do the arithmetic. I don't know if you were alive in 2001 or not. Maybe just barely. But I think you probably have a sense, like my parents did before me, of how Pearl Harbor was a real Pearl Harbor was a very impactful event on the lives of their parents. 9/11 was an impactful event on the lives of your parents and kind of on the country itself in both instances. The reason I have that image there is it's a good example potentially of how history might influence an experiment. I want you to imagine that you're doing a study on fear. Remember, that's what I do for a living. You're doing a study on fear and anxiety. And you start the study on Monday. You collect some data. Then on Tuesday, 9/11 happens. And then on Wednesday, you're supposed to collect more data. The difference between your participants on Monday and Wednesday with a big historical event on Tuesday. Any difference you find between them, is it a function of the experiment, the manipulation, or is it the historical event? Now, it doesn't have to be something so dramatic. It can be just something local, something individual. You can imagine on a college campus, you're doing a study on college pride, and in the midst of the study, over the course of the experiment, your college hockey team wins the national championship. Something like that. So it's when something outside of the experiment happens historically, societally, even locally, that may influence the result. That's history. Maturation. Maturation is the threat to internal validity where the normal change and development of your participants is really the cause of any change in variable B. Look, we talked about the potential ABC mouse experiment. And if I gave that ABC mouse to kids when they're 3 and then tested their reading when they are 6 and tried to argue the ABC mouse improved their reading scores dramatically, well, that'd be bollocks, wouldn't it? I mean, maybe ABC mouse helped, but what's more likely? What's more likely is the kid's normal maturation is the reason for the change. We can't argue that reading scores improved because of giving them ABC mouse, because they may just have grown up. They may just have matured. And that can happen with maturation. It doesn't have to be such a long period of time, by the way. If we're doing something like study skills as an experiment or a study, and I test incoming freshmen, and I compare them to outgoing sophomores, maybe if I had some sort of training session, I'd try to argue that that training session made the difference. But it may just be that you learn through normal maturation how college works and how to study if you're going to succeed over the course of that freshman year. So we can't argue that our intervention changed variable B because it may just have been maturation. That's a confound, and that's a threat to internal validity. Another common threat is testing. When we give a paper, pencil measure, or any kind of dependent variable, it's possible that our participants learned from that experience. That any changes we observe in our dependent variable, we're calling variable B here, is not due to our intervention, not due to variable A, but just that they've previously been exposed to the test. You think about this in elementary school, and you take a spelling quiz, then they give you some sort of intervention, some kind of practice, and then they give you the spelling quiz again. Scores improve. Did those scores improve because of the intervention, the practice you gave them, or did the skills improve simply because they've seen the test before? A less obvious example might be something like an MRI. A lot of researchers use MRIs. Our friends over at Brown in the psych department have an MRI that they get to use a lot. It's a very powerful, very expensive, kind of elite research tool. But it's open to this. Because to go in an MRI is kind of scary. You go inside this tube, it makes you anxious, it makes a loud noise. And the first time you do it, you have anxiety, you have fear, you have the discomfort of a novel event. And that's going to influence your result. Next time you go in, you've already been in there. You feel a little bit better about it. You're not nervous. You know how it goes. And that's going to change your response. That's okay. But it's possible that that change is what explains the difference between part 1 and part 2. Not some manipulation of your IV. Not some manipulation of variable A. So repeated testing matters. And honestly, anytime we see an experiment in which the participant is measured twice via the same event, what we sometimes call a pre-test, post-test design. We might see it in some sort of repeated measures design. Whenever we see that, we have to be very suspicious of testing as a potential threat to internal validity. Instrumentation. And this is really just measurement error. Whenever we see a change in variable B, it may not be because of our intervention. It may not be because of variable A. A may not be causing that change in B. It may simply be that we have inconsistency in our measurement tools. Even something like a scale. Look, I don't want to bore you with my life story, but I've had to be very, very cautious of my weight my whole life. I go up and down all the time. I have a problem with food. But I have learned over the years not to weigh myself every day because of the inconsistency in the measurement tool. Even a really expensive scale is going to be different a little bit every day, and you can draw unfair conclusions about what you did that day. Better to wait. Probably every 2 weeks is best. I do it every 7 days. So that those measurement errors are less likely to be the cause of any kind of change in my weight because I've had 7 days of any potential, variable change. If I decide not to eat potatoes for a week, that's a ridiculous example, but if I decide to eat potatoes for a week, not to eat potatoes for a week, I can wait to see 7 days rather than measuring every day where that measurement error is likely to be the actual cause. In psychology, instrumentation and measurement error is a real problem because we're trying to measure things we can't see most of the time. We're going to have some systematic error with a scale. We're going to have some systematic error with a measurement, like of a distance, right? But in psychology, because our tools are so imprecise, measuring personality, that measurement error is going to be really potentially damaging. It's also why psychologists have to use statistics so much. That's why probability is so important to us. Instrumentation also is what we call measurement error as a result of using different judges. If we have observers measuring some behavior, the difference between those judges is also considered instrumentation or measurement error. So if we see a difference between variable B, is it real or is it due to measurement error? We call that instrumentation. This is my favorite, called statistical regression. That's a painting by Van Gogh. That's not important, except I love it. But the reason I have that image there, that painting there, in the context of statistical regression, is I've often argued with my friends who are clinical psychologists, my wife included, that statistical regression is the best friend of a clinical psychologist. Let me read you the formal definition first, and I'll explain what I mean. Changes in variable B were due to statistical phenomena in which very high or low scores will regress towards the mean when they are repeatedly measured over time. What? That sounds fancy. It's not, actually. If you're super depressed, and I hope you're not, you might be. If you're super depressed, so depressed, in fact, that you, for the first time in your life, seek out therapy. You seek out that therapy, and then you take the depression inventory again, and it turns out you've gotten better. Did you get better because of that therapy? Or did you get better because you were so depressed that your score was so low that the only place it can go is up? It's that same frequency distribution we talk about all the time with probability. Your score on that measurement of depression was so severe that statistically speaking, it's not going to get any worse. It's more likely to get better. And that improvement is not because of therapy or any other intervention, but just statistical regression. A really, really high score on an intelligence test is likely to go down the next time you take it. Just probabilistically, right? A silly example would be something like if you were 7'2" and you had a son. The chances that your son is taller than you are very low. Not because of some weird intervention, not because of diet or anything else. It's just because you're so tall. You're in the 99th percentile that they're likely to be shorter than you, just probabilistically. Well, that's the same idea. Scores that are extreme, when remeasured, tend to go down. And we have to be careful not to assume that change in variable B is due to A but instead that it's just due to probability and what we call statistical regression. It's an important one, in psychology especially. Mortality, or as we call it now, attrition. And honestly, attrition is the better name, but mortality was the original name, and I'm so damn old it's hard for me to learn the new one, so I try to use both. And they actually flip back and forth, which is not great. I'm sorry for that. But if you see mortality in this context, think attrition. If you see attrition in this context, think mortality. The name makes sense. Mortality obviously refers to death, and it could be death. Attrition's a better word, though, because what we're talking about here is people dropping out of a study. Maybe because they died, but most likely because they quit. And attrition as a threat to validity is that what can happen is that people differentially drop out of your experiment, and it misleads you. Let's go back to that ABC mouse experiment, if you'll allow me. If we have a group that gets ABC mouse and a group that doesn't get ABC mouse, and think about ABC mouse in that group, say there's 50 kids. Well, the parents don't like it, the kids don't seem to play it, so the parents drop out, and we're left with 25 kids in that group. The 25 kids who stayed use it a lot. The 25 kids who left do not. So now when we actually calculate the result of using ABC mouse, it looks like it's really, really effective. Because the only people who stayed are the people for whom it was effective. So that matters. Now we have this kind of artificial understanding of what ABC mouse can do. Because only the folks for whom it worked stayed. That can happen in drug studies. You're giving a potential medication for a treatment, and those for whom the symptoms got better, they stay in the study. Those for whom the drug didn't work, they drop out. So you're left with this artificial understanding of the effect of the drug as a result of mortality or attrition. That's why it's a threat to internal validity. In some ways, this is the real granddaddy of all of these. And we've been talking about it in a different way this whole semester, and really much of last semester. Because what we're talking about when designing a study requires, excuse my stumble, that we sample our population. Because our population is likely too big to study. So at the heart of that, the logic of that, is that our sample represents the population. That's going to be true in experiments as well. Even more so. Because typically what's going to happen is we're going to sample more than one group. And so we need both of those groups to represent the population. And in doing so, be equal to each other. So selection is going to be a real focus of our attention here, moving forward. Let's apply these internal validity threats to a particular design. It's another one-group design, which we're kind of leaving behind here, but I want to take a step back before we take a step forward. Same logic, we take a single group from our population, presuming that our sample equals our population, and then we expose them to some manipulation of our IV. The difference is here we pre-test them on that DV, we're calling it variable B, then manipulate them by exposing them to variable A, and then test them again on variable B. This is a pretty common design, not so much in psychology, but other areas of social science. But it is rife with threat. For example, something could happen between the pre-test and the post-test that influences the result. The difference between the first test of B and the second test of B is not because of the exposure to A, but some other event. Maturation, if there's a long period of time between the first and second test, which might happen in college, comparing freshmen to sophomores, or in high school, comparing the first day of class to the last day of class. It could be maturation, not variable A, that matters. Testing, taking the test twice. We've talked about that. You're taking it before and you're taking it after. That could be the difference. And then finally, statistical regression, my favorite. If you have a really high or really low score that first test, chances are your second test will differ simply due to statistical regression and not necessarily because of variable A. So this design, which looks perfectly reasonable and, is reasonable, is not an experiment for all the reasons we've just described. It kind of looks like an experiment, and a lot of studies look like experiments. They're almost experiments, and so we call them by a different name. We call them quasi-experiments because they sort of look like experiments. They sort of look like you could develop causality, but it's only sort of. When you look carefully, when you look closely, you realize they're really potentially confounded by all those threats of validity. Excuse my sniffles. I'll try to edit that out, but I won't be able to. A group design in which a researcher compares pre-existing or naturally occurring groups. They're exposed to different levels of a variable of interest. We call that a quasi-experiment. That's the prototypical one. Anytime you see some study that compares men to women, for example, let me first say those are usually lousy experiments. Philosophically, using men as a control group for women is garbage. And there's a long history in psychology of doing stupid things like that. Using majority groups, white participants, as a control group for non-majority, for minority groups, that's garbage. It doesn't make any sense. But you see it a lot. You can't manipulate the ethnicity or the sex or the gender of your participants. And so as a result, it can't be a true experiment, even though everything else about it might look like it. So it's a very common version of a quasi-experiment because there are pre-existing or naturally occurring groups. So we'll spend some time talking about quasi-experiments. They have a role to play, but they can't develop causal relationships because of the threats to internal validity. Let me show you another example. It's a study that's more like what we're going to be doing moving forward in a very common methodology. Now, your textbook author calls this a two-group post-test only design. That's not exactly what Campbell and Stanley called it, but it's probably close enough. What we're talking about here is we have two groups taken from our population, and we expose them to different versions of our independent variable. Two different versions of variable A. And then we measure them to see the difference on variable B. And we presume that any difference is a function of our manipulation of variable A. Cool. Except that we have attrition to worry about. Maybe one group drops out differently than the other because of the manipulation, and therefore we don't really have a good picture of the result. But the real threat, the fundamental foundational threat in a design like this, is selection. And when we're talking about experiments, selection is going to be the granddaddy worry of an experiment. Because at the heart of this, we're presuming that both of these groups, group 1 and group 2, are the same to begin with. That we've drawn them from a population, both of them from a population. And because we've drawn them from the same population, they represent that population. And if they both represent that population, they should be equal to each other. And if they are, we can expose them to different levels of this variable and see the effect. But that's a lot of ifs. For this to work, they have to start out the same. So that's going to be a primary concern and focus for us when designing experiments. Speaking of experiments, I've been using some vocabulary that's come up earlier last semester, but it hasn't been formally defined this semester. It's a little bit sloppy of me. So let's get that done. First, we have the independent variable. And that's the variable in the experiment manipulated by the researcher. We have control over it, and we're going to manipulate it differentially between our groups. The idea is we can see if that manipulation manifests in a difference between the groups. We manipulate the IV differently, and we call that manipulation conditions. So we may have two conditions of the IV. If it's a drug, maybe there's a placebo condition and an actual drug condition. that manipulation is thought to produce a difference in our groups. And if it does, well, then we're going to try to argue that that is the cause of the difference. What is it we're measuring? Well, we're measuring what's called the dependent variable, or the variable in the experiment that is expected to be altered by the IV. By the way, it's called the dependent variable because it's thought to be dependent upon our manipulation. That's where that name originated. And basically, it serves to test the outcome of the conditions of our independent variable. So we have the IV, which we control and manipulate. We have the dV, which we measure to see the effect of the IV. That's the basic foundational bits of an experiment. So this is a diagram that kind of represents your prototypical two-group experiment. So the first thing we need to do, of course, is recruit our participants. Now to do that, of course, we have to select our population. And as always, that's up to us, what our population is going to be. And then we're going to find our sample. Now, your textbook spends a lot of time talking about different ways to get your sample. And we've already talked about that last semester, but I want you to pay attention to it. It comes back here again. Random sampling, of course, is going to be our Cadillac strategy. We'll talk more about that, but there's some other strategies as well. And then we're going to randomly assign them to groups. And the logic of this is that if we've sampled from our population, our sample looks just like our population. Now, if we take that sample and randomly divide it between our conditions, we should have two groups of our sample that look the same. So we're starting with equal groups. We then expose those groups to two different conditions of our independent variable. Maybe one group gets a sugar pill and one group gets fluoxetine. So we have just that difference. And then, of course, we work to keep everything else the same. That was number 3 on our list of causality. Trying to control confound variables and continue to strengthen our internal validity. If we're able to do that, and it's a big if, then the only difference between our two groups should be whether they got the sugar pill or whether they got the fluoxetine. And if that's the case, if we've managed to do that, then when we measure our dependent variable, any difference we see must be because of that manipulation of the drug, of the IV. The extent to which we successfully keep everything else constant is going to be the limiting factor in our ability to draw that conclusion. If we do a really, really good job, we have really high internal validity, then we feel confident. If we do a lousy job and we have poor internal validity, we don't feel confident. So this is the logic of experimentation, and every experiment we'll do all semester long. So your textbook author now goes through some practical issues when designing an experiment. And I don't want to review all of it. Some of it's pretty self-explanatory or redundant or not especially important right now. But I did want to say a few things. And I hinted at this a few slides back, but I want to pay some special attention to the idea of random assignment and its relative similarity to something we've already talked about, which is random selection. So if we have this population, this is like the 9th different picture of a cartoon crowd I've given you. But if we have some population, random selection allows us to choose a group at random from that population. And therefore our sample and our population should be equivalent. At least the probability is in our favor that they will be equivalent. And we've used this method to then test the effect of an IV on a sample compared to the population. But what we're going to do as we move forward is not this, but instead we're going to take that sample, we're going to divide it into two different groups through not random selection, but random assignment. Meaning we're going to take that sample and randomly assign them into two different groups. And just as random selection gave us a sample equal to our population, Random assignment should give us two samples, two groups equal to our original sample, which is therefore equal to our original population. So we're basically repeating that same step of using random assignment and the power of it to make our two groups equal. And it also made our sample equal to our population. Now we can manipulate those two groups differentially and see the effect. This comes from your textbook table 9.1. This comes from your textbook table 9.1. And you can see here it gives you some of this kind of the distinction, the juxtaposition between random selection of your sample versus random assignment to your IV condition. I don't think I need to walk you through this, but I wanted to point this out to you in particular. The one thing I will kind of point out, though, is the last one here on each side. It says, random selection of your sample increases external validity. It's been a good long while since we've talked about external validity. But external validity is the extent to which your result can be applied more broadly. And the better your sample represents your population, the more you can apply it. When we're talking about random selection, we're increasing internal validity because it's assuring that our two groups are equal to begin with. And if they're equal to begin with, then any manipulation that produces a difference, we can say with more confidence, is caused by our IV. So both random assignment and random selection are increasing our validity, just in two different ways. A word about ruling out alternative explanations, which, as I've said, is the really hard part here. If we have those two randomly assigned groups, we presume that they are equal. The probability is on our side that they are equal. And then what we do is we expose them to two different conditions or two different versions of our independent variable. One group gets condition 1, one group gets condition 2. Now the question is, are they still equal? And that puts us in the position of having the opportunity to talk about this in the context of our statistical hypotheses, which are going to look a heck of a lot like the same hypotheses we used for single sample experiments, except now we have two groups. So they look something like this. Our null hypothesis, which we used to predict that our IV had no effect. If our IV didn't matter, then we would predict that the mean of group 1 is equal to the mean of group 2. Because they started out the same, the manipulation didn't matter, so they should still be the same. The alternative hypothesis, of course, is the opposite. What we predict if we expect that our IV had an effect on our DV. And though our groups started out the same, now they should be different. So M1 is not equal to M2 because our manipulation of the IV, the differential treatment of our groups with that IV, should have changed them. They started out the same, they no longer are. And this basic setup, this basic design, is what we're going to be talking about in our next chapter, the between subjects, independent samples experiment. It's not the only experiment, though, not the only way this can play out. We might get something that looks more like this. We have a randomly selected group, but it's just one group. We expose them to condition 1 of our IV, and we get a sample mean on our DV. We then take that same group and expose them to condition 2 of our IV and get a second sample mean. And then we can compare those means. We get something that looks like this. The null hypothesis, again, is that our IV had no effect on our DV. So M1 equals M2. Our alternative is that M1 is now different than M2 because of that manipulation. So therefore, they are not equal. M1 is not equal to M2. This is another way to carry out that same experiment. But we're using the same sample as its own comparison group. The same people get exposed to level 1 that get exposed to level 2. Now, this won't work all the time. but it can work. If this were a drug experiment, IV condition level 1 could be the placebo. And then IV condition 2 could be the actual drug. And what that allows us to do is to keep our groups. We can guarantee that our groups are the same because it's only one group. We're comparing people to themselves, so we don't have to worry about our random assignment having worked. This is the chapter after the next, the topic after the next, although it's a long ways away because we spent a lot of time in independent samples groups. Independent samples experiments. An experiment like this is called a within subjects experiment or a dependent experiment. It's also sometimes called a repeated measures experiment. So just a little look into the future here. Another thing worth spending a minute or two saying a bit more about are the types of manipulations of our independent variable. And let me say this too. The stronger the manipulation, the better chance that your IV is affected by your DV. Or rather, your DV is affected by your IV, excuse me. And I think you know that intuitively. Let's use a drug study as an example though. If I gave you 100 milligrams of THC and compared it to a control, or if I gave you 1,000 milligrams of THC and compared it to a control, you would expect that 1,000 milligram study to produce a greater effect on your DV. But in that same example, we have to be mindful of the ethics of that. How strongly we manipulate things could make our study unethical. So something to keep in the back of your mind. Your textbook goes on to talk about some specific types of manipulations you can do. An environmental manipulation, which involves changing the place or the environment in which the study takes place between groups. Maybe one group is in a high humidity room, one group is in a low humidity room to see the effect of humidity on your DV. A very interesting and important method is called the Confederate method, the Confederate manipulation. This is not a reference to the Civil War, thankfully. The word Confederate just means friend. The South called themselves the Confederates because they were a group of friends. Sorry, my Yankiness came out there in my sarcasm, but it deserves sarcasm. But a Confederate in this context is talking about you having a secret researcher that pretends to be part of the study who actually carries out a manipulation. So in the very famous Solomon Asch study about social influence, there were a bunch of Confederates who were purposefully giving the wrong answer to see if that would cause people to also give the wrong answer. They were part of the experiment as researchers, not as participants. So they were the ones in charge of the manipulation. They're called Confederates. Scenario manipulation is very common, where you're using a story to set up a scenario, a vignette, and you simply change the story. Maybe in one story you say that your waiter wears a mask when they bring you your food. The second story is exactly the same, except that person doesn't bring a mask. That's you're manipulating the scenario through changing a vignette. Instructions, you can give two different sets of instructions as a form of an independent variable. And you really can't do this, but I do all the time. Physiological manipulations, where I give an animal a drug, where I maybe do a manipulation of a brain region via surgery, and see the effect that has. But not everything is manipulatable. That is very hard to say. I have this is called manipulate this, sarcastically. Manipulate this, like it's a threat. And this comes from your textbook. It's a series of potential independent variables. Can you manipulate these things? Can you manipulate the weather? No, I don't have superpowers. Neither do you, probably. Can you manipulate a room color? Sure. Can you manipulate a participant's ethnicity, socioeconomic status, or different ableness? These are things that come with the participant to the study. And they cannot be manipulated. I want to emphasize that. These participant characteristics, and not just these, yes, ethnicity, SES, disability, but also intelligence, shoe size, ice cream flavor, hometown of origin, religion, all of these things, which might be important to your study, can't be manipulated. Which means it's not just you. Nobody can manipulate them. So that means that anytime you see a study in which they draw causal inference about things like ethnicity or SES or disability, you should call Bravo Sierra on that. Because they weren't able to manipulate that. So they don't know if the result they found was due to those things. That's the point of an experiment, right? So I want you to be head on a swivel and ears open for that. Because people do that all the time. Sometimes because they're just bad at understanding scientific method or bad at reading scientific papers. It shows up on the news in this way. But also sometimes because people make bad faith arguments for political purposes. So I want you to be careful about that. What about Confederate sexual orientation? Look, you can't manipulate my sexual orientation. But if I'm a Confederate, I can pretend. I can be an actor. So even though I'm straight, if I were being a Confederate in the study, and for the purposes of the study, it would be useful as a manipulation for me to be not straight, then I could do that. I could declare myself not straight. And in that instance, that would be a way of manipulating my sexual orientation as a Confederate. So there are ways to do things like this, but we can never manipulate our participants' personal characteristics, of course. So if we're going to try to study something like that, whether it be ethnicity or SES or something else, we have to use quasi-experiments. And again, that means we absolutely cannot in any way draw causal inference. One more thing, and I think I mentioned this in passing earlier in the slides. Psychology has a sad history, and really, society has a sad history of comparing ethnic groups, majority and minority ethnic groups, and treating the majority group as the control group, as if that's the normal. This is the standard. And then saying, look at the difference here as a result of ethnicity. First of all, you can't say that because it's got to be quasi-experiment. But second of all, you can't treat the majority group as the control group, as if they're normal and everything else is some kind of weird variation. That's not how people work. So it's bad science and it's also just bad humanness. So yes, you can have comparison groups, but please, please, please keep in mind, remember forever and ever, that just because there are more white people than there are Latinx or African American people, that doesn't make white people the standard that you use for comparison for everybody else. No, I'm talking about that in science, but you should hold on to that outside of science as well. Okay, enough about that for now. All right, so that's kind of how this works conceptually. We talked about some specific types of experiments, but we're going to go into great detail. It's one thing to understand how a car runs, but it's another thing to try to build an engine. So you might have some sense of how this car runs, the car that is psychological science and causality. But now we got to go through the actual tools, the equipment, the method. We're going to do that kind of one method at a time, talking about how an experiment like that would work, and then actually learning how to do the statistical analysis. That's why our next chapter we're working on for a very, very long time, because we need to learn the method, we need to learn the statistic, we need to learn to do an SPSS. And I actually have to do that twice in one chapter because there's two different techniques. All right, let's get to it.
Time travel! What? I see this as an absolute win.